Good morning, everyone. Now, this is the second part of our refrigeration. So we will be looking at the modification to the reverse Carnot cycle. Now, due to the impracticalities of reverse Carnot cycle, we have what we call a simple vapor compression cycle. And from the simple vapor compression cycle, we have either is superheat or it is with superheat and undercooled. So this is the second part of our refrigeration. So here, this is your vapor compression cycle. Now the condition is dry saturated. When you refer to this point 2 here, the point 2 at this point here, where point 1 to point 2 is actually in the compressor. So point 1 is the compressor inlet and 2 is the exit. So here you have point 2 as dry saturated. So we have this vapor compression cycle, which is dry saturated. So it's just the same. The only thing different here, it is being replaced by an expansion valve, okay, instead of a expander, okay. Now, just the same here. So state point 1 to state point 2 here, you have isentropic compression. So that is where you have your work input. So to find the work input here, you have to take H2 minus H1. So the next one is your state point 2 to 3. That is this part here. Yes, you can see it is at constant pressure from point 2 to 3 and also at constant temperature at this point 2 to 3 at this condition. So 2 is actually your condenser inlet and 3 is the condenser exit. And then you have 3 to 4, that is where it goes into the expansion valve, where we say it is an irreversible throttling process, 3 to 4. So for throttling processes, we have the constant enthalpy, that is H3 equals to H4, okay? So this part here. So the irreversible throttling process. So where 2 to 3 is a constant pressure heat rejection. And then 4 to 1, okay, is your constant pressure heat absorption or the refrigerating effect. So simple. Now, when you want to find work in, you just take H2 minus H1. But, okay, so when you refer to your property tables, you have to see what type of refrigerants that you are referring to. Now, most of the examples that we will be looking at or our tutorials is based on, okay, R134A. So based on the property tables, you have to search, okay, your H1, which is wet vapor, okay, and then H2, H3, and H4, which is equal to H3. Okay, so H1 here, okay, shows that, okay, the vapor compression cycle is still not a perfect type of cycle, because where you refer to point 1 here, as you can see, it is actually at the region of liquid and vapor mixture. So, and we know that compressor can only be dealing with one phase or single phase. Either it's a pump or a compressor, so only a single phase. But here, when you refer to this point 1, it's actually two phase. That is with liquid and vapor. So this is another limitation of the vapor compression cycle. Later on, it will bring us to what we have that is called the superheated vapor compression cycle. So point 1 to 2 here, that is isentropic compression. Then 2 to 3 is your constant pressure heat rejection. And then 3 to 4 is your irreversible throttling process. And then 4 to 1 is your constant pressure heat absorption. So work in, just simply take H2 minus H1, okay, and then heat rejected, okay, and then your refrigerating effect for this section. Okay, so when you look at this point 1 here, as I've already mentioned just now, okay, there is a limitation of vapor compression cycle. So therefore, you have later on, what we have is the superheat vapor compression cycle. So the schematic diagram is actually based on the same schematic diagram, but the only thing is when you refer to this, your point 1 is dry saturated. Where if point 1 is dry saturated and if it goes according to isentropic compression, so your point 2, as it touches the condenser pressure line, it should be superheated. Okay, so then 3 is saturated liquid, and point 4 is actually the mixture of liquid and vapor after the expansion process. Okay, now superheat with undercooled. So when you look at this part here, okay, this is where you have your undercooling process. Undercool takes place, okay, that is within the condenser. Okay, so since, okay, if let's say for example you take a look at my laser pointer, the red point here on the pressure condenser pressure line on the superheat with undercooled vapor compression cycle, you look at the laser pointer that I put here. Okay, so in actual practice, your actual point 3 should be here, as what I am showing on the laser pointer. Okay, so in actual cases, it should be that. But due to the improper data that we have got in our property tables, not improper, that means not enough. Okay, so what we do is we actually shift the point 3 instead of this point here to point 3A here. So we consider that as the actual point. So what we can do is if we want to find H3A, so H3A, then we will have to look at the undercooled temperature. That means, or the subcooled temperature. Sometimes the questions will give us, okay, that the temperature is being undercooled by 12 Kelvin or 10 Kelvin or 5 Kelvin. So what you need to do is you need to take the saturation temperature of the refrigerant at the condenser pressure minus, okay, the degree of undercooled. So if let's say, okay, the temperature here at T3 is let's say 30 degrees C, then your point 3A, let's say they say undercooled by 10 K, so 30 minus 10, so that means here should be around 20 degrees C. Okay, so that is how you can find H3A here based on the temperature that you have found earlier. Okay, through the example, you'll be able to understand more. Okay, so compressor inlet now become dry saturated. Now compressor deals to, now the compressor now only deals with single phase, that is dry saturated vapor. So the work in is still H2 minus H1. Then you have your heat rejected, the same. Okay, and then your refrigerating effect should be H4 minus H1 here. Then for undercooling, so if you want to find the temperature at point 3A here, because you need to find the enthalpy, so that is why you need to find the temperature if the questions give us a degree of undercooled. So what you need to do is you need to take the saturation temperature T3, which is based on the condenser pressure, minus the degree of undercooling. So you will have T3A. Then from T3A, you'll be able to find out the enthalpy H3A later on here. Okay, so your H3A based on T3A. And then H3A is equals to H4, remember, because that is a throttling process there. Irreversible throttling process. Okay, so your heat rejected should be H2 minus H3A. It's no longer H2 minus H3. Then your refrigerating effect is H1 minus H4. And remember, your H4, once, let's say, for example, you got your H3A wrong, then your H4 definitely will be wrong also. Okay, so you have to be careful how you're going to determine the H3A later on. Okay, so RE is actually the refrigerating effect or the cooling effect. Okay, vapor refrigerant undergoes a change in temperature before it undergoes latent heat of vaporization. Okay, in the RE, okay, in the evaporator. Now here you have some tutorials, 1, 2, 3, and 4. Actually, you have 6 of them. Okay, so the other 2 is on the other page. Okay, so this example will be shown later on in my later slide. Okay, that's all. Thank you.